Okay, so today we're going to look at carboxylic acids and we'll find out about the naming and their structure, so how to name them and what's unique about their chemical structure. We're then going to find out how we can, what their physical properties are, so their solubility, their acidity, and you might want to also think about boiling points. Also, how we can make them, how we can prepare carboxylic acids from other compounds, and their reactions. Okay, so first we're going to look at their structure, the functional group that defines carboxylic acids and its shape. So you'll notice there are three areas of electron density around that central carbon. So trigonal planar arrangement, so 120-degree bond angle. And then the bond angle around the oxygen is 104.5 degrees because you've got two lone pairs on the oxygen and two shared pairs, one going back to the carbon and the other one to the hydrogen. Okay, so how can we name them? Well, the naming rules follow the same kind of format as for alkanes. So you find the longest carbon chain first, so that's your stem. Then you replace the end, so ethane, with oic, ethanoic. And this defines the fact that you've got the COOH functional group. Then you start your chain numbering from the carbon on the carboxylic acid functional group. That's carbon number 1. Any prefixes? Well, your prefix is going to be your longest carbon chain, so meth, eth, etc. And then any side chains, they're numbered according to their position relative to your COOH group. Okay, so let's have a go at naming a few carboxylic acids. So here's methanoic acid. And this is page 1 of your notes. Display formula would be C double bond O, OH, and just a hydrogen coming off the end, because meth, 1 carbon, and oic acid because you've got a carboxylic acid group. Next one we'll see is benzoic acid. Slightly more complicated. This is a new kind of structure for you. So we've got the benzyl group, which is essentially a benzene ring, and instead of one of the hydrogens on the ring, we've got a carboxylic acid group. So the C double bond OH is coming off one of the carbons on the benzene ring. And the benzene ring is delocalized. So remember, you've only got one hydrogen on each carbon, and all those bond lengths are exactly the same length. They're not quite a double bond, they're not quite a single bond. Okay, now I'm going to draw out the displayed formula for an acid. What I want you to do is have a go at naming it. Okay, so have a go at naming this carboxylic acid. Remember, you've got 2 carbons in the longest carbon chain and you've got 2 oic acid groups. Okay, so have a go. Fill in the table on page 1 of your notes. Okay, so this is, your prefix is going to be eth, because you've got 2 carbons, and it's ethan 1,2-dioic acid. Okay, so well done if you got that one right. Also have a go at drawing the structural and skeletal formulae of that acid in your notes. Next one, I want you to draw the structural, displayed and skeletal formula for benzoic acid. So have a go at doing that in your notes first, and then I'll go through the answers with you. Okay, so the displayed formula is simply 4 carbons because you've got bute, and we've only got 1 oic acid group, and that's on carbon number 1. And then remember to put all the hydrogens in as well in a fully displayed formula. skeletal formula, the join the dots. So we've got 4 dots, and then at the end of our dots, which are joined together, we've got RCOH. And then the structural formula is just going to be CH3, CH2, CH2, COOH. Okay, good. So give yourself a big tick if you got that right. The next one, and for this one, I'm going to give you the name. And again, you need to have a go at drawing the structural, displayed, and skeletal formula for 2,3-dimethyl pentanoic acid. So pause the video and have a go at doing that in your notes now. Okay, so the structural formula is HOOC, CH, and then bracket CH3, because you've got a methyl coming off the second carbon, and then a CH, and then bracket CH3 on that third carbon, and then CH. Oh, there's a slight error there. It should say CH2 and then CH3. And then the skeletal formula, again, the join the dots, carbon number 1's where our COOH group is on, and two side chains for our 2 methyl groups. And then the fully displayed formula should look something like this. So make sure you've drawn all your bonds on each of your carbons and between all the hydrogens. Don't get sloppy with the displayed, always show every single bond in a displayed formula. Okay, do remember that structural formula should have CH2, CH3 at the end. Okay, the next one, I'm going to give you the displayed formula for this acid, and I want you to have a go at naming it. It's also got a double bond in it, so the stem is going to have an ene in it, so remember about that. And also think about the properties of the double bond, the fact it can't rotate. Okay, so have a go at naming this one. Alright, you should have realised that the 2 carboxylic acid groups, they're both on the same side of the double bond, which is on the second carbon. And you've got 4 carbons in total, so Z, butene, because of that double bond, and then dioic acid. Okay, because we've got 2 acid groups. You should also be able to do the trans or the entgegen version of the E version of that one as well. So have a go at drawing out the structural, displayed and skeletal form for the entgegen one. Okay, let's have a look at another one. Okay, so this one is the structural formula this time. H3C, CH, CH3, CH2, COOH. Okay, so have a go at naming this structural formula. Alright, you should have named it by now. And the name should be, well, you need to first of all count your longest carbon chain. We've got 4. And then look at the side groups. So 3 methyl, because the methyl's coming off the third carbon. And then butanoic acid, because we've got 4 carbons, butanoic acid. So the prefix, the 3-methyl, remember that's coming off the third carbon. And the examiners love to give you these formulae back to front, where you have to write your numbering of your longest carbon chain from right to left. So do take care in the exam over those ones. Alright, so the next thing we're going to have a look at is their physical properties. So, carboxylic acids, well, they're quite soluble in water if there's a shorter carbon chain joined onto the oic acid group. Now, you have a think about why you might think they're soluble in water. And they're also acidic, as the name might suggest. And this is a property of their functional group and how easily it loses the proton on that COOH group on the OH part. Okay, so why are they water soluble? We'll have a look and think about the intermolecular forces. What type of intermolecular forces do you think exist on a carboxylic acid group? Alright, so we can see we've got an oxygen bonded to hydrogen, and that's bonded to the carbonyl group there. And we've got the delta plus and the delta negative on the carbonyl group, and a big delta negative on the oxygen and a delta plus on the hydrogen. Water can form a hydrogen bond, a strong hydrogen bond with that OH group on the carboxylic acid group. So you can draw a hydrogen bond there. You can also get hydrogen bonds between the carbonyl group and a neighbouring water. The non-polar part of the carboxylic acid, I've circled it here in blue, will have London forces between it. So that will dissolve better. So if you've got a larger, longer carbon chain there, it has more London forces relative to the amount of hydrogen bonds it can form. So it's got strong London forces, so those are less soluble in water than a shorter chain carboxylic acid, like this example, ethanoic acid. Okay, so we've got a permanent dipole there. I've just labelled all the intermolecular forces on our diagram. So hydrogen bonds. And I've also tried to show a hydrogen bond between the carbonyl group and an H2O. It's not strictly speaking a hydrogen bond. It's really a permanent dipole hydrogen bond, but it tends to be classified as a hydrogen bond in your textbooks. Okay. Alright, the next thing we're going to have a think about is the whether or not, what sort of, how soluble the another type of carboxylic acid group is. So this one is benzoic acid, and it is soluble in warm water but not cold water. Have a think about why it's a lot less soluble than, say, ethanoic acid. You can form this one hydrogen bond between your OH group and a neighbouring water. So it is weakly miscible, but remember, when you dissolve it, you're going to also have to break and put in energy to separate those strong London forces between the large non-polar benzyl group. Got a lot of electrons there, so there's going to be relatively a lot of London forces, so that's going to take a lot of energy to separate those versus the energy released when you form your new hydrogen bonds in your water, in your solution of water and the benzoic acid. Okay, so the key things you need to think about with solubility is how big the non-polar group is and how many hydrogen bonds each carboxylic acid can form. Okay, so the next thing we're going to have a look at is how between carboxylic acids we can also form hydrogen bonds. And this is why they're quite soluble with each other. So you can mix a variety of carboxylic acids to group and they'll form these relatively strong hydrogen bonds between the oic acid groups. This also means they can have an anomalously high boiling point compared to, say, an isoelectronic alkane or a non-polar compound that only has London forces between it, because we've got these strong hydrogen bonds and it's going to take a lot of energy. When you boil something, you have to put in energy to separate the molecules so you can turn it from a solid, liquid or whatever into a gas. Okay. So we've had a look at solubility, but now what we need to have a look at is the acidity, one of the physical properties of carboxylic acids, the acidity of carboxylic acids. Okay, so carboxylic acids exist in equilibria with something called the carboxylate anion. Okay, and this is the negative version of the carboxylic acid which doesn't have its proton on anymore. Now, the carboxylate ion is very stable. It forms if you look at how it forms a delocalized structure, and the negative charge of the carboxylate anion is spread over the two oxygens. So if we actually look at a crystal structure of carboxylic acid like this, you'll see that the bond lengths between the carbon and the oxygens are the same. And this is indicative that you've got this delocalization, and that's essentially where the lone pair on the oxygen, you've got two resonance forms which I've shown you on the top right of the slide, and they exist 50-50 mix all the time, and on average you're going to have this bond length which is a symmetric molecule essentially. So the stability of that carboxylate anion is the reason why it's so acidic. The more stable that ion is, the more acidic, the further right, if you like, to the equilibrium, this the dissociation of the carboxylic acid is going to lie. Okay, so how acidic are they? Okay, how can we work out how acidic they are? So if the ion, the carboxylate ion, is more stable, so less negative, less reactive, then your acid strength is going to be more. It's going to be a stronger acid. It's going to dissociate more readily. You're going to form that negative ion with more ease, therefore releasing those protons. So it's a good proton donor. So the stability of this ion is determined by what group's attached to the carboxylic acid group. If you've got an electron donating group, you're going to be donating more negative charge into the anion. So that's going to be making it less stable because it's more negative. Whereas if you've got an electron withdrawing group, something pulling away the electron density from the carbon, then you're going to have a more stable carboxylic acid, the ion, if you like, because you're going to have your protons being more likely to be lost, as the ion can exist quite happily without its proton. Okay, so think about electron withdrawing groups. Electron withdrawing groups are going to be groups that want electrons. Electron donating groups, remember which ones those are. They're things like long alkyl chains and anything that's quite happy to lose some of its electron density. Okay, so let's have a look and a comparison of a couple of carboxylic acids and their relative acid strength, how readily they lose that proton on their OH group. Okay, so the first one we'll look at is methanoic acid, that's on the left. And on the right you've got ethanoic acid. Okay, so we've got an electron donating group on the ethanoic acid, that methyl group's donating electron density into your carbon. So that's making the positive dipole on the carbon a bit smaller and the negative dipole on the oxygen a little bit smaller. Therefore, the positive dipole on the hydrogen is a bit smaller and it's less likely to be dissociated, the OH. Okay, because the bond got more covalent character, if you like. On our methanoic acid, the hydrogen can't donate that many electrons into the carbon. So there's much bigger dipoles on the carbon delta plus. We're more likely to lose our proton and form the relatively stable carboxylate anion. Okay, so that's the more acidic. The methanoic acid is more acidic than the ethanoic acid because it hasn't got as much electron density being donated into the carboxylate anion, so it's less negative, if you like. All right, let's compare another couple of acids, carboxylic acids. Have a look this time at, well, this is benzoic acid. It's anion. I've actually drawn the anions this time. So this is the anion of the benzoic acid, so the benzoate ion. And we've got electrons being delocalized into the ring. Okay, so the benzene ring is accepting electron density. It's able to take away that negative charge from the carboxylic anion. Whereas if we look at the ethanoic acid on the right, we're going to compare benzoic acid to ethanoic acid, its actual anion. You see that the methyl group's actually donating more electron density into the negative ion. So the electrons are pushed towards your delta plus carbon, and so it's more negative, therefore less stable. So the more acidic one of these ones is going to be the benzoic acid. Okay, so how can we make carboxylic acids? Well, if you remember, we can make them from oxidation of primary alcohols and aldehydes. And it's the full oxidation reaction, so we need to do this reaction under reflux with excess acidified sodium dichromate. So I've just drawn the two ions there, the acid and the chromate ion. We can also make them by hydrolyzing a nitrile. Okay, a nitrile. Now this is a new molecule for you. A nitrile is an R group attached to a carbon with a triple bond N. Okay, and we will also need, when we do the hydrolysis of a nitrile, so remember hydrolysis is addition of a water molecule, we'll need an acid and H2O. We can also do base hydrolysis, so for that one we'll need a base and H2O. Okay. Alright, so we'll go through the reactions. Oxidation, you just need to go and review your notes over that. You should be able to fill this in on your notes. So if you look at the moment, we are in page 3. Okay, so you should be able to work out how to prepare prepare carboxylic acids from primary alcohols or aldehydes. Come up with a method, that's AS. Okay, so I'm going to go through the hydrolysis of a nitrile. First of all, we're going to do the acid hydrolysis. Okay, so to the nitrile, we want to form the carboxylic acid. So I'm going to draw the product first before I balance my equation. So there's our carboxylic acid, and we also lose a molecule of ammonia. We're going to need, if you look on the right, we've got 2 oxygens and an extra proton. So we're going to need 2 molecules of H2O, and we're going to need an acid catalyst, and we'll do that under reflux. Check your equations are balanced. You might also be interested to see that the carboxylic acid will quite happily exist as its anion, and we can form the ammonium ion as well. That's in equilibrium, if you like, with those 2 products. So either of those 2 sets of products are correct chemically. It depends how electron withdrawing your R group is on your acid, how much of it's dissociating into its sort of negative anion that I've drawn on the bottom right there. Okay. This is the base hydrolysis of a nitrile. So instead of using an acid, we're using a base to add that H2O to the carbon which originally had that nitrogen attached to it. Okay, so we start off with the nitrile and we add hydroxide ions, and we'll also need a molecule of water. And the first thing we form is our carboxylic acid anion, our carbanoate ion, and we'll also form a molecule of ammonia. We then, if we want to form the full carboxylic acid, we're going to have to add an acid to the product, and then that proton, a strong acid like sulfuric acid, and then we'll form our carboxylic acid. So the base hydrolysis is done in 2 steps. Step 1, you add the base and the water and form the the carboxylic acids anion, or the carboxylate ion. Okay, so now what we want to find out about, we've looked at how to make them and what can we make from carboxylic acids. The first reaction you need to know is what happens if you add neutralization reaction, adding a base, sodium hydroxide. Remember, you make the, when you add sodium hydroxide, you're going to make the sodium ethanoate ion and H2O. Then what happens if you add sodium carbonate? Well, again, you're going to make the sodium whatever, O8 ion, okay, and CO2 and H2O. What happens if you add PCl5? This is where you make acyl chlorides, and HCl is also released, and you also get POCl3. And then what happens if you add an alcohol to them? Well, this is how you make esters, those lovely sweet smelling compounds that are used often in perfumes and sugary sweets. So add an alcohol and you can make an ester. Okay, so that's the summary of 4 of the reactions. There's also reduction, which I'm going to do on the next slide. But just make sure you know in general how to make neutralization reactions with a base, and how you always get the RC double bond O, O minus, Na plus. You get that sodium ethanoate ion being formed, and then the carbonates, what happens there, you always, again, you make that sodium carboxylate ion group that way, and the acyl chlorides with the PCl5, which are used in lots of reactions, and that we can make esters by adding an alcohol. Okay, alright, so let's have a quiz. Well, not a quiz, let's have a look at reduction first of all. Reduction with metal hydrides. So this is where we reverse. Remember, we oxidized alcohols to make carboxylic acid, so guess what? When we reduce them, we go back to the original alcohol. So whatever you could make the carboxylic acid from, you can now reform with reduction. And you need a sort of hydride ions for this to happen. And this is where the lithium aluminium hydride comes in. Okay, so that's LiAlH4. And then at the end, you're going to have to hydrolyze it to make the full carboxylic acid, because in the first step, you form that carboxylate ion, just the C with the 2 O's and the negative charge delocalized all over it. Okay, so that's nice and balanced, and have a look and make sure that everything's balanced. We've got the same number of protons on the left hand side as we've got on the right hand side, and you lose a molecule of water as well when you reduce a carboxylic acid. Alright, so we've had a look at the types of reactions, and now I'm going to do a quick quiz. So I'm starting off with a carboxylic acid, and I'm adding sodium metal to it. What does this make? Okay, so what does this make? Write out what general product you would make when you add sodium metal to it. Okay, here we go. You're going to make the carboxylate ion with a sodium plus attached to it. If you wanted to name it, if the R group would say, if it was ethyl chain, it would be sodium ethanoate, okay, or sodium propanoate or whatever. And we'll also get hydrogen gas with sodium metal, pure sodium metal. All right, another quiz, another question. This time we're going to start with ethanoic acid, and we're going to react it with PCl5. What does that make? Okay, so pause the video, work out what you think it's going to make. Okay, so if you worked out that it made ethanoyl chlorides and HCl and POCl3, you get a gold star. Well done. Okay, so that's ethanoyl chloride. That's how we name the acyl chlorides. Next one. Let's have a look at this one. Well, we've got, looks like we've got, what's that? You should be able to know it, name it. It's 1,4-butandioic acid and sodium carbonate. What is that going to make? Have a think. What's that going to make? All right. Well, with that, you're going to make the, again, the carboxylate ions, anions at either end of the chain, and a sodium ion is going to be attracted to that negative anion, and you're also going to have the H2O and the CO2 release. So you're going to see effervescence. This is a good test for carboxylic acids, a very good test for them, because alcohols will not react the same way as this, so you could differentiate between an alcohol and a carboxylic acid this way. So that's disodium butandioate. Next reaction, let's have a look. Oh, we've got, that's benzoic acid coming up on your screen. What's going to happen when we react that with an alcohol? Woo! So have a think, what's that going to make? All right. Well, when you have an alcohol and a carboxylic acid, you make an ester. So instead of the hydrogen, you've now got the R group from your alcohol. So we've made benzyl ethanoate. Okay, so benzyl ethanoate. The end always ends at the bit which is going across, forming the ester group, which is the single bond O then joined on to another carbon. So that's the functional group of an ester. Okay, another reaction for you. This time we've got your favourite, butanoic acid reacting with PCl5. What is that going to make? Well, so pause the video. Okay, so that's going to make your acyl chloride. And that one's called NaHCl and POCl3. So that one's called butanoyl chloride. Butanoyl chloride. Acyl chloride. Excellent. All right. Next one. Have a go at this one. This is, oh, again, butanoic acid, except we've got two methyl groups on it. Okay, so that's 2,3-dimethyl butanoic acid and lithium aluminium hydride. What is that going to make? Okay, so draw out your products and then we'll go through the answer. Here we go. Alright, so you should have worked out this is a reduction reaction. So we're going to go back to the original alcohol, our nice primary alcohol there, and we're going to also lose a molecule of water. So have a go at naming it as well. So that's 2,3-dimethyl butanol. Well done. Hopefully you got that. Okay, so finally we'll just summarise, and this is also on the last page of your notes, of your carboxylic acid notes, which is on page 5. So we should now know how to do naming and structures, what they look like, and their bond angles, their physical properties, so their solubility, their acidity, trends in acidity and melting points. Preparation, how do we make them? And the chemical reactions. And there are 4 chemical reactions you need to know. So neutralization, esterification, making esters, and reduction with lithium aluminium hydride, so back to the original alcohols, and what happens when we react with PCl5, so making the acyl chlorides. Okay, when you've done your summary page, your revision page, you're happy with that, make sure you've then filled in all your notes, and the next thing we're going to look at in the next pack is going to be carboxylic acid derivatives, so what we can do with carboxylic acids and their derivatives like acyl chlorides, etc. Okay.